Hello and welcome to the podcast According to Sci-Faith, where we discuss topics revolving around the compatibility of science and faith. I'm Joshua Göcking and you're listening to According to Sci-Faith. Preview of the episodes 17 to 20, Where are the bugs? Episode 17. Do we live in a simulation? So this question is around for some time now, so many people think about it. There were many movies made about it, and it's also in science it has come up several times. There are scientists who really believe in this so-called simulation hypothesis, where we say that we might be living in some kind of a computer simulation where everything we experience, even our innermost being, our thoughts, our mind, our consciousness, is itself just part of some huge simulation. And I think today I wanted to go after this question: do we believe it's true, or why is it true? Is it true, or what can we say about it? Or to say it bluntly, why do I believe it's nonsense? So let's go through it, and I want not only to talk about why I don't believe in it, but also why I think ideas like this, or ideas in general, where I believe they are kind of nonsense, even if you cannot prove anything about it, why I think that these ideas seem to be so present in these times, and what could be the cause of it. And so we also will dive into literature about this, so it will be really exciting. So stay tuned. And so let's just start by talking about the what we mean by living in a simulation. So I mentioned it's just like being in a big computer simulation. So it's the idea is there is so much computing power, or there's a society there where there is so much computing power that we basically can simulate everything and without any problems. And then there might be a society like this who would really say, hey, we want to simulate events before of the past, we want to replay the past, and so on, and they start such a simulation. And the question is it probable that we would be part of such a simulation? Is it likely that we would live in such a simulation? So first of all, let's consider how that idea might have come about. So when we consider the beginnings of science, we see if you think about the beginning of modern science, it's mostly started with people like Isaac Newton and so on. And if you look at the worldview that Isaac Newton had, Isaac Newton thought the world was just like a big clockwork, a big mechanical clockwork where everything fitted together, one screw fitted into the other, and everything worked out perfectly. And for him, for Newton himself, this even was a big show that, or a big sign that there has to be a God. So in his work, in his great scholium, he states that such a perfectly fine-tuned universe, such a perfectly clockwork, can only be possible if there's a designer behind it, if there's a God behind it who created it, such that everything works out perfectly. So of course I am paraphrasing freely, but if you are interested, I recommend to you to read the great scholium of Newton. It's really really good or really interesting what he writes there, and really shows you what his mindset or what his thinking was behind all this. So now we go into the future, so we just stay in this time. We look at how long was this worldview around, and it's been around pretty long. So the worldview that was brought by Newton has been around for a long time, and for the most part because it's been really, really effective. Science could be described in a really good way by this worldview of Newton, that everything has a cause, that we believe that still, but that also, if I know the initial conditions of something, I can perfectly describe the whole system, and I need only to have this and know the physical equations that describe the system, and then I can compute everything, then I can predict everything, and there's nothing coincidental happening, no accidents, nothing, so I can describe everything basically by those laws. And this has been around for a long time. So by the 1900s, it was still very much believed that the world really exactly behaves in this way. The one problem that this worldview has, although Newton was convinced by this that there has to be a God, it still limited the kind of God there could be, because if one would think it further, which people later did, especially in the 1900s, it would yield to this idea that everything would have to be determined. So the way of every particle, of every atom would have to be completely determined, which of course led to this conviction that, okay, if this is the case, then also every particle in our human body and in our human brains would have to be determined from the beginning of time. And therefore, if we were therefore also determined in our thoughts and in our thinking from the beginning of time, how could then something like free will exist? So this was a big conundrum that came up then, and this could not be easily solved. I mean, you could, of course, if you just assume that there is more to humans than their material being, then you can easily solve that. But it was quite something that people struggled with and that people had problems with. But what happened then is, then in the 20th century, or with the beginning of the 20th century, there came new theories about, and one of this theory was quantum mechanics. And in an earlier episode, we were talking about multiverse and quantum mechanics and interpretations of such, and there we already saw hinted at this that there's a probabilistic nature of quantum mechanics that changes this whole Newtonian worldview, where we are no longer in such a perfect clockwork, but where the world is still really fine-tuned. So it's in this fine-tuning sense that Newton had, it is still a very much perfect clockwork, but there are probabilities that play a role all of a sudden, and not probabilities in a statistical sense that you say, okay, we have so much particles, it's just easier to make predictions about using statistics instead of looking at each atom individually, which it is just impossible to do. No, now there are real probabilities that are occurring that we cannot, where we cannot predict what will happen. We can only say, okay, to a certain probability, such and such will happen or will not happen. And this was the big change or game changer that quantum mechanics brought. And most of all, it was really counterintuitive. While Newtonian's worldview was in some way intuitive, it came intuitive to the thinking of the people at the time, and also it comes, if you learn about it in physics, it comes intuitive to you. Once you learn about quantum mechanics, it really goes against the intuition we have about our world. And there was another theory for which this was similar that came about at about the same time, and this was the theory of relativity that Einstein came up with. And here it's that the statements of the theory, they are easy to understand, I think. I mean, you just have to assume that the speed of light is constant everywhere, and you can easily derive that from statements that really do make sense. But the results of these statements are still very counterintuitive, where you have all of a sudden time behaving differently depending on how fast you move relatively to each other. So there's this popular twin paradox, which really clearly shows this. So where there are two twins, so twins who are, and the one twin is like an astronaut, and he's traveling around space with speeds close to the speed of light. And on the other side, there is the other twin, and he's, let's say, just some accountant who's in his office all the time, does not travel much, and so on. And so they live their lives, and in the end, it will be that the cousin, the twin who is the accountant, he will age much more fastly and than the other twin. So because for the twin who is traveling a lot close to the speed of light, time will pass more slowly relatively to his twin. So for him, he experienced time the same as the other twin would. But if you compare them, if the other twin looks at his twin brother, he sees him aging slower because of this consequences of the speed of light being the same in every system. So these results were really odd. So on the one hand, quantum mechanics and later even quantum field theory, and also the theory of relativity. So, and I think what you saw then was people were really starting also, so especially older scientists who were used to the Newtonian worldview, they were really rejecting these ideas, the theory of relativity and quantum mechanics. Even Einstein was not really comfortable with quantum mechanics at first, so they were really rejecting these theories, and because they were going against their philosophical convictions, but they turned out to be wrong, right? Because today we know that the world actually behaves in such a way. As we had in these earlier episodes, there are still many people who have different interpretations of it, and it's still highly debated what the true interpretation of those theories is. But still, we know that there is some truth to that description of our universe, and therefore those scientists who were rejecting these ideas were wrong. And I think this led to somehow believing so while these older scientists were wrong in thinking a theory that goes against my intuition has to be wrong, I think today it's sometimes switched in the other direction, where we say no matter how crazy a theory sounds, it could in principle be right, and therefore I will not reject it, which is in principle also right and of course true, because if something is not it can be proven then and is proven, then we have to accept it. But I think there is still the danger to go too far into that direction, where we see stuff that cannot really be measured, cannot really be shown to be true, and we accept it as something of value, or even where things where we kind of know that the world shouldn't behave in such a way, but because we say, I don't want to be of the ones who think it's crazy, and in the end I'm the one who was wrong in all this. So therefore I think people tend to stay away from such predictions. But I think that in the end it's important to also have still go after some intuition. The problem is the intuition has to be right, or it has to be founded on the right principles, and also one has to be, of course, flexible. But I think it is a mistake if one goes too far into the direction where everything goes and everything could possibly be, because then you might waste your time on theories who are complete bogus and complete baloney. And therefore I think there needs still to be some distinguishment between what theories do really have merit and which ones do not. And I think especially with such hypothesis, such hypothesis, in my opinion, like, do we live in a simulation? They make for a good sci-fi movie like The Matrix, and there you can pack a lot of great stuff in it. So it's also one of my favorite movies, nothing wrong with that. But I think if we look to it as a theory of as something, if it is really true, if we really live in a computer simulation, I think there's easily you can find reasons why that might be wrong or why that is not the case. And therefore I want to make it obvious that I don't believe in such a hypothesis, and I think it's, to my opinion, sometimes a waste of time to really go deeper or be occupied with such ideas. And also I think it shows a greater thing about how theories come about in these times and why there might be a problem with it. So first of all, but let's look at the argument that is presented why we might be living in a simulation. And one of the greatest scientists behind this, or who is convinced of such a simulation hypothesis, is Nick Bostrom, and he states that there are many works of science fiction, he says, that forecast such technologies where such a thing is possible, where the computing power is so hugely advanced that it will be possible to to code such a simulation, to create such a simulation, super powerful computers who can do this. And what we would do in this science fiction novels, if we do it, we would look to our forebears. We would simulate what they did, and so therefore we have to assume that this is done. And if this is done in some future, then there is still the possibility that we are in such a simulation, and this is highly probable. Then he argues that this is the only way in which this is not the case is if one of these assumptions is wrong. So either we do not achieve such a future where this is possible, or we would not simulate something of the past if this were possible. And I think he's right in this, and I think where this is true is that the assumptions are wrong. That's in my opinion, because I do not believe that such a simulation would be possible. Especially, or more than that, I believe that such a simulation would not be possible for humans. Because the first questions, and I think the most important question, which is also the title of the preview for this episode, is that comes about when this is discussed, is where are the bugs? Where are the bugs? So if you're not familiar with software development, a bug in the software development is usually an error or a mistake in the code where something has not been considered. And if you run the code or the program and you come to some point where you click on something and then there is nothing to handle this issue because it was by mistake or by somebody did not consider this use case, and then all of a sudden the program crashes or some unexpected behavior occurs or whatever. And if you are familiar with software development, but even if you just use your smartphone daily or your computer daily, you might have recognized that sometimes your apps crash or something occurs, and this is just because there are in all our software there are still bugs. So everywhere where we have humanly programmed software, which is all the software there is, there are some bugs in it. There are some mistakes in it. Something that were not predicted when the software was implemented and could not have been known to the developers. And usually this is not a problem because these bugs can be quickly fixed. But there are also some severe accidents that happen because of it, so it's not a small thing, especially in parts where there are severe things that can happen. But what the important thing is that these bugs occur everywhere. So I mean, if you ask a company, if you are looking for a software developer or software company that develops bug-free software, this is just not happening. The only way to achieve that would be to not develop any software. Then it's completely bug-free for sure. But that would not be of any help. So in my opinion, the fact that we do not observe in our world any kind of bugs is the greatest statement that we cannot be living in such a simulation that was created by humans. You might say, or sometimes in science people might experience stuff or find stuff where they say that for this we have no explanation. Why is this needed? Seems to be completely arbitrary or completely useless. But usually later we find out, this is the cause of it, this is the purpose of it, and it really is needed, and without it, nothing would work. So most of the time, even if we find something which one might call a bug, we find out later, no, that this is in fact a feature. So this is also a sentence from software development. It's not a bug, it's a feature. This is something that most of the time you say it cynically. If some software development firms develop something which you think to be buggy, but they don't fix it, and they say it's supposed to be like that, and there you say, okay, it's not a bug, it's a feature. It's supposed to be this way. But in the creation, it's actually this way that when we find that it's not a bug, it's a feature, that we really begin to appreciate a feature because it is then a real feature. And we expect usually in science, then your horizon is expanded to why this is needed and why this is useful and why it is in such a way. But you don't find a bug. So, and therefore, this is my greatest argument for why I do not believe such a simulation hypothesis is true. More than that, if you think further, so let's just assume that there is such a simulation. So we have seen there are no bugs in this simulation. Apparently, in our simulation, if we are in one, there are no bugs. So it cannot have been a human or a human company or something that has developed such a bug-free system, because that's not possible. So the next question then would be, who was it? So it would need to have been a perfect developer. And this is not very different from what you would call a god. So then the question is, where is this really different from believing? So I saw this tweet, I also retweeted it, this was really funny, of somebody who was saying about the simulation hypothesis, said, yeah, you believe we live in a simulation, yeah, actually you just believe in God, you just think he's a nerd. So I found this was really fitting to what it really is. So because a simulation always assumes that behind any simulation there has to be somebody who designed it, right? Somebody needs to design the simulation that you have. So if you play a computer game, there were some coder, some designer, some software development team, some game development team that designed all this. And the same way it would be in such a simulation, more than that even, that there would have to be someone behind it designing it. And how much more shows this that there has to be some god who is designing it, especially if you see there are no bugs in it, so the designer has to be perfect. And the only difference that you then find between such a simulation and I call it real world, where we are not simulated, but where we are free agents living in a created world, the only difference then would be actually that what I called it, free agents, free will, that we have free will and that our decisions have consequences on the world in which we live, because it is not simulated, it is real, to say it like that. And I think that's also the thing that this kind of idea tries to escape. It tries to escape the responsibility. It tries to say, yeah, we are just living in a simulation, and what we do does not have any consequences, is not of consequence. It's just a random simulation, and we are part of it, and let's have fun in it or whatever. And I think this is not the case here. So I think it really is that we have free will, that we are created with free will from God, and that our decisions do have consequences. One question that would also occur, of course, or to me at least occur, is if we are living in a simulation, and the designer, of course, he has complete control of the simulation. He can, if you imagine, he can, run processes more or less freely given the initial conditions, but he would have more or less complete control over the simulation. And why would he want the simulation to know that it is living in a simulation? You can pretty much argue that he would not want his simulation to find out that it's living in a simulation, because whatever he's trying to do with the simulation, whatever he's trying to simulate, the simulation itself, knowing that it is simulated, would work against this purpose. And therefore, one more thing is, I think you can think of it like that: if we really would be living in a simulation, we wouldn't know that we are living in a simulation, and we wouldn't be able to even come to the idea that we are living in a simulation. So I think that's a further strong argument against this, and I want to also see this is not really science. It's called a simulation hypothesis. There you see it's not even a theory, it's a hypothesis. And the reason for that is there's no way to prove it. There's no way to show that we live in a simulation as being part of the simulation. There's no way to do that. And therefore, we are not arguing in science here. We are more or less talking about philosophy. Do we believe that we are living in a simulation or not, or more of this kind? And I think this shows also what I was talking about in the last episode about the limits of science. And it shows here we are clearly beyond the limits of science, and therefore it is also nonsensical in a scientifically way to seriously talk about whether we live in a simulation or not. But if you say, okay, what do I care? Science, not science. I want to know if I'm in a simulation or not. So it's more about finding truth. And to state this clearly, finding truth is not only done by science, or in my opinion, cannot only be done by science. There is, as I said, a limit to science, and there are truths that cannot be found by science. There are several arguments I did also on my blog where I state this. So, for example, in mathematics, you can find this from a proof of Gödel, where he basically shows something like this in mathematics, but I want to do not want to dive too deep into that. There's a blog post on my Substack where you can read more about that. But what I want to find is, why do we come to this idea? Why do we, as philosophical beings or human beings who think about philosophy, come to this idea that we might live in a simulation? Where does this come from? I mean, if you look at it, I think this idea seems to me rather new. It seems to me rather becoming in the last century, coming up in the last centuries. And the question is why? The question is, why does such an idea come? Where does it come from? Where does it stem from? Why would one want to live in a simulation, or want to have such a philosophical worldview of living in just a simulation, or many other ideas? I'm not talking just about such ideas, many different ideas, mostly materialistic ideas that, for example, also state that consciousness is nothing but neurons firing in our brain, and then at some point something like a consciousness emerges. How do these ideas come about? Why do we have not a deeper understanding of it? And I think one point comes from an effect that also brought science itself about, but it also is a negative effect of an altogether positive thing, as I believe. And I think this came also with the, as I already said, with the emergence of the scientific method and all this beginning of modern science. I think this was mostly triggered also by the Reformation, because as we know, the Reformation occurred at a similar time. And I think this was really connected, that with this new thinking, also new thinking in the area of science occurred. And you see this also in the case that many of the reformers or reformed thinkers were also scientists, for example, Johannes Kepler, and also not only scientists, but also scientists who are now belong to this group where we think they had a part in creating this scientific method. And therefore, I think there's really the connection there. And if we look at it this time from there, so I think if you look from it from a believer's perspective, you see that before there was a lot of superstition, a lot of, even in the church, so a lot of superstitious beliefs and so on, and also many things where if you compare what people believed with what really the Bible says, where this also deviated, and where there was a lot of corruption in the church and so on. And therefore I think this Reformation that came about with Martin Luther was really necessary and was really needed to reform the church, to bring the church back to biblical convictions and to biblical truth. However, this had an effect on society, because if you look at it, society is usually for society, the church, what the church said was the truth. So what it was their standard of truth. And when the Reformation came, there all of a sudden was not anymore this one standard of truth, but now all of a sudden there were two competing theories or two competing statements about what the truth actually is, two competing institutions, even if you will, who were competing about what truth is. And with the Reformation, of course, more and more other competing institutions came about. So there were several groups or directions of believing. So this led also to many negative things. Most importantly, to wars. So and in the end, you had this 30-year war where basically they fought about this and. In the end, they came to the conclusion to say, okay, we won't argue about this anymore. Everyone can, in his area of authority, so for the kings and fiefdoms, there was basically they could decide which religion they would uphold to, which kind of Christian belief they would uphold in their region, and they would leave each other alone, and believers could decide in which region they want to live and live according to where they could live out their faith. So this was basically also the birth of federalism, and so, but this was, as you see, it was kind of a stalemate. It was kind of something where we just, okay, we agree to disagree, and so this was not really the solution. This is what often is called the Peace of Westphalia, and it led to there not being a complete standard of truth anymore. I mean, it was an improvement because now nobody was being killed anymore, no wars anymore about something like this, but still, I mean, if one could see, it was just something like, we won't argue about this anymore because arguing is no help. And I think there's one thing that is covers this pretty the whole. There's one play that covers this really good, the whole thing that happened there with this changing of the standard of truth, or with all of a sudden a competition of what truth really is instead of this one standard of truth. And this is from William Shakespeare, and it's Hamlet. So it's probably one of his most famous works, and there are many things in it. It's really hard to read and to understand, but there is really a lot of stuff in it. It's really enriching to read it and to see it. So if you can, I really recommend it to watch it played, for example, in a movie, and then you can also read it. For example, if you read it, the vulgar versions are really helpful. They add a lot of notes to that. And if you really want to what I find was really interesting, if you really want to know the difference, or what kind of a difference nonverbal communication makes, then I encourage you to first read it and then watch it, and then see how much more you understand of the play by just watching it. But that's just a side note. And but I really encourage you to read it because there's a lot of in it. But the basic story is, so there is this, it's in the Kingdom of Denmark, somewhere in the Middle Ages, I guess, and there is this Hamlet. He is the son of the king, and the king, so he died, and his mother, the mother of Hamlet, so the wife of the queen, he kind of immediately after he died married his brother, who is now the king. And at first Hamlet struggles with this, his mother immediately going to the next guy basically, and later he also encounters the spirit of his father, who says, I did not die of natural causes, but I was killed by my brother, so I was poisoned. And he asks Hamlet to revenge him, or take a revenge on him. And from that point on, Hamlet kind of goes mad, intentionally, as he suppose. So he wants to camouflage or disguise himself or his intentions with acting like he's mad and be acting crazy, acting madly. And in this in this part he speaks out all kinds of things that might sound familiar also in theories today. So there's a lot of you can find in there a lot of things of postmodernity. For example, he at one point he says there's no good or bad, but thinking makes it so, and so on. So he puts all these ideas that are pretty common in the time afterwards, in the time after that came up in the time after the Reformation, in all these philosophies, and there you can see that. And there are many ways to interpret this play, and I think there are many ways people have interpreted it, and I think there are many possible ways to interpret it. But I think one I saw was really where he related it to really this happening of the Reformation and the effects of this Reformation, especially on society. And this can be also that Shakespeare himself had this in mind, can be also seen by the fact that Hamlet himself is actually not in the play. He's living there in the castle in Denmark, of course, but actually he arrived from Wittenberg, where he was studying. And if you know about the Reformation, you know Wittenberg was basically the center of the Reformation, where the Reformation happened, where everything occurred. So it's kind of the birthplace of the Reformation. So Shakespeare seems to intentionally have created this link to the Reformation there. And if that was his intention or not, you can argue about that. But I think really you can see it in this way, that through these the Reformation, as good as it was, as it brought us as I believe, really back to the Word of God and to the truth of the Word of God, and showed the importance of Scripture and of being justified by faith. As important that was, the effects it had on society were it had also negative effects on them, because all of a sudden there was not anymore this one standard of truth, but there was competing standards of truth, and the problem that occurred with that was that people or that several ideas could not be distinguished anymore easily anymore. You could not, if you had some crazy idea, you could not say, okay, is this idea good or bad? You could not. Usually you would maybe go to your church, say, okay, is this idea good or bad? And then you would get an answer, and you would continue in this way. Of course, if you know the history about it, at that time, that the church was pretty corrupt in some places at least, and so if you might have gotten a right and true idea and gotten to your church to find the truth, and they would say it's false. So it was necessary to replace that, or to put this competing in, but it was, I think, not the perfect solution maybe, and had this negative side effects. And as you can see, there are all these ideas that are already mentioned in Hamlet began to spring up. So you have these postmodernist ideas where truth is supposed to not exist anymore, or that there is no truth, there's only power, and also there's no good and evil. Just what we believe to be good and evil is just basically random ideas that we get from somewhere, and so on. All these ideas that came up mostly in the 19th century, but they were already in there. And I think this is what happened due to this many competing ideas of truth. And I think in science it was similar. It is especially since this basically this worldview of Newton fell apart, where before we had the Newtonian Newton's axioms, we had basically his worldview of this perfect clockwork, and where every scientific idea that we tried, we tested on okay, is it in accordance with Newton's law? And if it wasn't, we usually quickly rejected it. But all of a sudden we saw, okay, no, we need to reject the assumptions Newton made. We need to reject the assumption that time and space are absolute, and we need to say, no, there is relativity. Or we need to reject the assumption that everything is determined by its initial conditions and allow for probabilities, and therefore for quantum mechanics to occur. And I think with this change, all of a sudden it was not anymore this one great encompassing field that on which we could test all theories, or if our theories made sense before we even test them, but now all the theories could possibly be, and then we have just any idea could possibly be, we just need to test if it's true. And I mean, we have still this testing mechanism that we can test whether it's true or not. That's good. So we are not completely lost, but I think it's still the case that there are many theories that come about this way that only until they are proven or until they are falsified are rejected, and I think this is a lot of time is lost this way. And I mean, it's one thing to say, okay, we are losing a little bit of time, that's not that bad, but if you are, for example, if you leave fields for of physics and go to other areas where it really would impact people, like theories of economics and so on, where what you decide on, depending on the scientific theory you have, really affects the life of people, then I think it gets more serious. And there it would be helpful to have some, to not have to try out your theories on human beings, but to really have something to distinguish that does this theory really make sense? Does it make sense to do it in this way, or is it maybe, even if there's no scientific facts about it, is it maybe, can I somehow still see that it is nonsense and not try it out on something with and doing possible harm to it? So therefore I think this is important and to distinguish there. And what I think is really the standard of truth that we can really apply is really the Word of God. I think that's really our standard of truth, the Word of God revealed by the Holy Spirit. And I think that's where we can stand, and where everyone in his personal life can say, okay, if I concentrate on this, if I let myself be guided by that, then I will save myself the trouble of going through ideas that are nonsense, or going through theories where I in the end find out that they are complete nonsense. So I think this is the solution to this dilemma. I think that we really go to the Word of God, go to what he says, because his truths are eternal, as has been shown in history over and over again. And therefore, if we stick to that and stay on this and not let this become corrupted, of course, because that's what happened with the church. They were not sticking to that because of different reasons. Things got corrupted. But I think if we stay on that, and if each one individually decides for himself to stay on that, to stay true to the Word of God and stay on his word, I think then we can save ourselves the trouble of believing in some theories that in the end turn out to be complete nonsense. And this is also not only helping to not waste time, but in some cases it's really helping to avoid harm. So I really want to encourage you to dive deeper into the Word of God with this. And if such theories come about, such simulation hypothesis, or what is consciousness, some theories how some machines or computers might get conscious or something, then really I urge you to dive deep into the Word of God and get your guidance from the Holy Spirit, instead of these ideas that are more or less scientific, that are flowing around the airwaves. Episode 18. Quantum gravitation, where is the problem? So, I several times already wanted to talk about quantum gravitation. It's not really my type of field. So if you know the German podcast, which you probably don't, but if you do, then you know that we talked about everything leading up to that point about quantum mechanics and general relativity. How can they be combined? But even if you don't know about this pretext, I think you can easily follow along with this introduction I want to give today. And in the next time, I just want to dive deeper into that topic, dive into the theories that come about now. Then we will also look into duality soon, and then I want to also look into theories like string theory and so on, and also look at the problems that these theories have or face, or why they are not confirmed yet or still considered to be not accepted or not widely accepted yet, and what the state of the research in these cases is. So, but if one wants to, so the question, of course, is, okay, quantum mechanics came about like in the 1920s. The theory of relativity even sooner. General relativity came about at 1915, and even the further theories, quantum field theory, was about in the 60s and 70s. It was formulated in its fullest. So why hasn't there happened something since then, or has there happened something? Why do we have not this complete theory of quantum gravitation yet? Why could we unite or quantize every other force than gravity? And of course, for one thing, gravity is much weaker than all the other forces, which is kind of funny, because if you look into it, the first force you experience in life or every time is gravity. You experience it all the time. It keeps you in your chair. It was also the first force that was scientifically described, and the first force people were really aware of. And the next one was, of course, electromagnetism. And only later we became aware of the weak force and the strong force. But the interesting thing is that the direction in which we became aware of these forces is exactly the opposite to the strength of these forces. So gravity is the weakest force. Then there's the electromagnetic force, the weak and the strong forces. So actually, that's not completely true. The weak force is the electromagnetic force is stronger than the weak force, but not because of their coupling, but only because of that the weak force has heavy gauge bosons. But that's complete. If you don't understand anything of that, that's just a side note. So, but I think that's an interesting concept, that the weakest force was actually is actually experienced the most, and the strongest forces we do not really immediately recognize. Okay, actually you do, because the electromagnetic forces and strong forces and so on are also responsible for you not going through walls and so on. So you kind of experience them, but you experience them not as directly as you do gravity, for example. Okay, but that's only a side note. And so this is one thing why you might say, okay, that this could be on a subatomic level. Gravity plays no role. It cannot be measured there. So maybe that's why we cannot unite it with the other forces. But we want to look deeper in what a real problem is if we write out the equations and put in the physics that we know about quantum mechanics and general relativity, and why this becomes a problem. So what we need to first show is we need to have these things. Okay, what about quantum mechanics? What do we use? So first we have this Heisenberg uncertainty principle that we will use, and then we have this statement that in quantum mechanics it's the case that everything that can happen will have a certain chance or probability of actually happening. And from relativity we take this the statement that energy is mass, so E equals mc squared. And many people get hung up on this c squared, but this is actually just a constant of proportional, so you can easily throw it out. So that's actually what theorists do. They say we choose our units such that the speed of light is equal to 1, and then this equation becomes pretty simple, E equals m. So this is saying that mass is a form of energy. And then we also use a statement of general relativity where it says you can make you can create black holes by putting a lot of stuff in a small place. So if we look into these statements, so first into the Heisenberg uncertainty principle, what does it really state? And what it does state is that you cannot simultaneously measure the momentum and the position of a particle to an arbitrary accuracy. So if I know that the momentum is basically the momentum the particle has, it's classically it's the mass and the velocity combined, and this is basically its speed combined with its mass, and then the position of a particle. And if I know, for example, the momentum, then I really don't know where the particle is. If I know where the particle is, then I don't know its momentum, and there's this uncertainty in both these quantities. And there's another version in which you can formulate this. For example, you can equivalent to momentum and position, there is this uncertainty in energy and time, and from this you can state that it is possible to borrow free energy from empty space as long as you pay it back within a short period of time and nobody is watching. So this is basically if you have this uncertainty of energy and time, this means you have an uncertainty in energy and an uncertainty in time. And this also means that there can be no perfect vacuum, because there also needs to be some fluctuations in the energy, because otherwise you would know the energy perfectly well and would know that it is zero. But it cannot be. Therefore, there needs to be some fluctuations about the energy. And therefore, even in the most perfect vacuum, there will be particles popping up into existence and annihilating each other, which we call quantum fluctuations. And this is basically what I described before, that you can basically take energy from empty space, from nothing. Basically, you can borrow it, and if you don't keep it too long, therefore there comes the time aspect, then you can keep it, and then you can have to give it away again. So, by the way, just I'm following here in this the slides of somebody from King's College in London. His name is Eugene A. Lim. So his slides on this topic I'm following, and I will put these in the description also if you want to follow along. So now we look in quantum mechanics. So we just look at an electron traveling from left to right. And what then can happen is it can, as we have stated, it can borrow energy from the nothing, from the space basically, and emit a photon. It can let a photon go out, like radiating it from itself. Now, this energy, it has, of course, after some time, it has to give it back. So it has to reabsorb the photon, and after some time, and then everything is fine, energy is conserved, and we are in good physics again. So what then happens, you have kind of a loop. So the electron travels, it gives out the photon comes back to the electron and is absorbed. So you have kind of a loop there. And these are called quantum fluctuations, as I just said. And if you have seen sometimes the diagrams that are used in quantum field theory, you might have seen such loops of photons, of wiggly lines, and so on. And this is actually what's going on there. This is such a loop, and these are called virtual particles, and they are virtual in a sense that they are not real, in a sense that you can really measure them, but you can really measure their effect. So these loops, they lead to corrections to the amplitude that we calculate in quantum field theory, and there actually we need to include all possible energies, including even infinite energies, and this is done by adding up all these kinds of loops that can be created there, and summing this all up will give us this amplitude, our result. And so basically, if you ask what really happened, what really of these possibilities of particles being emitted and absorbed, or even two particles being emitted and absorbed, or one particle being emitted and it itself emits particles and is absorbed, and so on. What of this is happening? And the answer is all of them at once, and in some kind of way, and the probability of any process is the sum over all these possibilities. This is, if you remember the path integral formalism that we in a previous episode already discussed. This is basically what's behind it. It's basically the path integral formalism in quantum field theory, that all these amplitudes need to be summed up together and builds the whole probability of this process occurring. And if one sums it up, and there are certain possibilities what can occur. So the first possibility is that we will get a finite number. And if this is the case, then that's wonderful, because then our theory is complete, and then we can continue. Another possibility is, of course, that we get a number which is infinite in its size. So this number does not converge to some value, but it gets infinitely huge. Then we have a problem, because infinite numbers in physics do not make any sense. That's we cannot use that, because it's not predictive. We cannot predict anything from an infinite number. So when we have this, when you have infinity, we know something in our theory is not working. Our theory is not predictive. And what we know then is that our theory might be incomplete, so there might be a problem with it. And this can be seen by a radioactive decay. We have beta radiation, where an electron is emitted. So basically what occurs there is a neutron decays into a proton and an electron. And since this, I don't know if we discussed it in the English podcast, but this is not if one particle decays in two particles, the energy spectrum of this would be discrete. But the energy spectrum of the radioactive decay is continuous. Therefore, you need a third particle in this process, which is called a neutrino, which basically takes care of energy conservation. But if you have this process that we look into, so a neutron and a neutrino decaying into a proton and an electron, so we have this process, and we want to look into the quantum fluctuations, if we can make it work there. And as it turns out, if we do this, we will receive an infinite result. So this is one example where this theory we have does not work. So what do we do now? Do we need to avoid this theory? Do we need a new theory? What can we do? But I mean, as we have seen, without the quantum fluctuations, we describe the physics, right? So everything is fine unless we include these quantum fluctuations. So that in a certain limit, something needs to go wrong. So maybe it's not completely wrong, but only incomplete. The theory is incomplete. There's something happening that we are not keeping track of. So let's try to fix this theory. Instead of throwing it away, let's try to fix it. So again, we consider an electron that emits such a virtual photon that it reabsorbs. But now we're changing something up. Now we say there's another electron, and instead of the photon being absorbed by the same electron that also emitted it, this time it is absorbed by this other electron. So one electron emits a virtual photon, and this is absorbed by the second electron. So if you, as a side note, this is actually how forces do work. So on a subatomic level, forces work in such a way that if two electrons are coming closer to each other, I mean, we know they repel each other because they have different charges. And the way this works is that one electron will emit a photon, which will the other a virtual photon, which the other electron will absorb, and this way they know, oh, okay, there's somebody coming against me, and they will repel each other. This is how forces works, and therefore the photon is not only a light particle but also the force mediator for the electric force. But it's only a side note. So we now have this process where one electron emits a photon and another electron absorbs this virtual photon. So absorbs this photon where the energy of it was basically borrowed from space. And now we assume that in our Fermi theory, which it is called this theory of radioactive decay, something similar happens. So instead of a neutron and a neutrino decaying into a proton and an electron, we have a neutron and a neutrino who exchange some new virtual particle we call W, and out of this exchange they decay into a proton and an electron. And yet now we know from special relativity that energy is mass, and so from this we can use the energy that would be needed for this particle W. We can use it to say that's the mass of this particle. So or the mass of this particle can be produced by the energy we borrow from space. Basically, this virtual particle can come into virtual existence, so to speak. And if we postulate this, then we find that we need also the existence of several more particles like a Z and an H. H is for Higgs. And if we recalculate everything, then we see that these infinities disappear and our theory is now complete. But for this, we need very massive particles. So the W, the Z, and the H particle would need to be very massive. The Higgs particle, for example, so the H particle is 125 protons heavy, and the W boson is about 90 protons heavy, and the Z 80, or I think it's the other way around. But so they are very, very heavy, which is, as I mentioned before, the reason why the weak, because this is the weak interaction, is actually weak. It's actually weaker than the electromagnetic one, although it actually would be stronger in its coupling. But that is again a side note. So now these particles could also be observed at a Large Hadron Collider in CERN, or the Z and the W were observed in a synchrotron particle collider also at CERN in 1983. The Higgs was discovered in 2012 at CERN at the Large Hadron Collider. And with this complete theory, this is now the complete theory of electroweak interactions, and it has been highly successful and predictive. So the principle we used here is we had some theory, then we checked this theory if it gives finite results. If it makes finite results, then we check it in experiments if it's correct. If it's correct, great, we are finished, Nobel Prize coming. And if it's wrong, then well, we have to find a new theory. But if we have infinite results, then what we do is we do not give up there immediately, but we add particles with a big mass to this theory until the theory yields only finite results, and then we check it with the experiment, and if it works, great. If it doesn't work, okay, then we really have to find a new theory. And so now let's look into general relativity. Let's look into how we can deal with that. So in general relativity, as we know, this is the theory of gravitation. And so we have to find something to describe gravitation with. So in gravitation, as it was discovered in recent years, there are these gravitational waves which long have been assumed to exist, or which completely also follow out of general relativity. And those would, on a subatomic level, they would be a particle, and this particle would be, we call a graviton. Which has not been observed yet, of course, but it's some particle that's going, for example, in the same sense as we described before. We imagine this graviton is going from left to right. And again, we will there have these loop corrections. We will have the particle omitting some other particle, maybe even another graviton, and absorbing it again, and so on. And then we check with all these loop contributions what kind of results we will get. And as it turns out, we will get infinite results. So we will get contributions that are infinitely big, and therefore general relativity obviously only works if we ignore quantum fluctuation, so no quantum gravitation there. So maybe our theory, as we assumed before, is incomplete and we can fix it somehow. So let's try to fix it. And what we do is, again, we again assume two gravitons, and now they exchange this particle, this virtual particle, which we call P. So we have this hypothetical virtual particle, and we want this to come in there, and now we want to compute as before which energy would be needed for such a virtual particle to come into existence and lead to finite results. And as we find is that this particle needs to be really, really, really heavy. So on the slide, he has there a number of 1 with, I think it's 18 zeros, and then this times the mass of the proton. So it is a really, really heavy particle. But for now, we say, okay, so the particle has to be heavy. What's the big issue with it? But now there is the statement from general relativity coming in that says if we put a lot of mass in a small area, this space will curve so much that it becomes a black hole. And actually the mass of this virtual particle we defined here would come in this area where it is so heavy that there would a black hole be created. And what's the problem with a black hole is that a black hole is also called a singularity, and this is also a version of infinity. So with this new particle, we get a black hole and infinities, and the black holes exist, but their existence makes our quantum theory non-predictive. So we win nothing with it, and our theory will not be predictive in any way. So this is the real problem. So why is it hard to unify quantum mechanics and general relativity? So for one, because quantum mechanics says that you can borrow so much free energy from empty space that the general relativity would then say that you make a black hole. And if you now ask, yeah, okay, but black holes exist as we do know from observations in space, so what's the problem with it? But the existence of these black holes make this quantum theory non-predictive because we have singularities and infinities, and there's just no way to make proper predictions from those. And therefore, that's the reason why it is so difficult to find a theory of quantum gravitation. Okay, it's time for a short break. Maybe you have heard of it, but recently Elon Musk told about his new research of his company Neuralink about human brain machine interfaces, where you basically with your brain you can access a computer or a smartphone or some apps and so on, and where they were showing first results of these experiments that they did. What I think is really interesting about this is that my book that you can order now also in English, Alien Thoughts, is really about exactly that topic, about some neurochip that is implanted in the heads of people and with which they can do similar things, and also with some side effects that occur in those. So what is even more funnier than this, I wrote my book, the most part of my book was really finished before I even know about Elon Musk's company and about what they were doing, and even knew about the name of this. And in the end, if you have read my book, you notice in the end there is some, I think I call it neural connection there, that they have there, and this is something that they use the neurochip for, with which they can do some stuff. So read it if you want to know more about it. But the interesting thing is, in the beginning, I planned to call this a neural link, and only when I found out that they were really working on such things and that a company that is working on it is actually called Neuralink, I decided to change the name a little bit to don't make this association to this company. But I really think it's interesting that something that I really had in my mind, only I was thinking about it, in some not so distant future it might come. Yeah, the future of this is not even as distant as I thought it would be. It's even closer in some degrees. I hope not the future that is described in this book, but still I think it shows that it's a pretty current theme, pretty current also in the technologies that are described there. So if you're really interested in scientific topics or sci-fi topics, then I really encourage you to read it. And also it's not a pure science fiction novel. It's also a lot of spies and of adventurous stuff is in there. So if you enjoy these kinds of novels, then I really encourage you to read it. And I would really like if you would order the book. And of course, if you have already ordered it and read it and you liked it, then I would really encourage you to write a review, such that other people will know what the book is about and can see if this book is something for them. Episode 19, The Physics Behind Oppenheimer. So last year, I'm not sure if you have seen it, but last year this movie came out of Oppenheimer from Christopher Nolan. And when this episode comes out, the Oscars were just awarded, but since I pre-record the episodes, I only know that this movie has been nominated for a lot of Oscars. So let's see how many Academy Awards it will win. But I think it was really a good movie. I really liked it. But as it is with such movies about physics, about from the view of a physicist, about an area of expertise, oftentimes the things one is most excited about is not covered there. For one thing, because the movie focuses on different things. I think in this movie, if you have seen it, it focuses a lot more on the politics and the implications of the development of the atomic bomb, and less on the physics of atomic reactions and so on. But still, it was a really entertaining movie. But I thought in this episode I can kind of add to that the physics behind the atomic bomb. How does an atomic bomb work, and what are the physical laws behind it, the principles behind it, and also some things that that interests me about, or would have been interesting to me about the Manhattan Project and the scientists behind it. So, as we heard in the last episode, basically what atomic bombs and nuclear weapons work with or what they use is basically radioactive decay. And in the last episode, we already talked about this to some degree in order to show it as an example of a theory where the infinity results of it can be removed in it. And there we saw also this process of a neutron decaying into a proton and an electron neutrino, of course. And this is also what occurs in there, where the process of nuclear fission is used. So in radioactive decay, this occurs spontaneously. Basically, the atom is in an unstable condition and it decays into a more stable one, and by this radioactive decay is emitted. But one can also stimulate that, and this is what happens in nuclear fission, where for example, you use then a neutrino, and you charge it on some of these particles, for example, uranium. Another material that can be used is plutonium. So these are the atoms that can be used for this. And with this shaking that comes from this neutron that is put into this atom, the repelling power of the electromagnetic force of the protons is then becoming stronger than the forces of the nucleus, because they have only a limited reach. And with this, the nucleus is split apart. And what this reaches is not only that then now we have two nuclei, but if one just checks the masses of the first nucleus and the two nuclei individually, you will see that the mass does not sum up. So what does this mean? Does this mean energy is not conserved? No, not at all. As we have learned also before in the last episode from the theory of relativity, energy is mass. E equals mc square, or E equals m if you put c to 1. And this is what's happening here. So the mass is converted into an energy. So actually the inner energy of the coupling of this nucleus is set free in this reaction. And so energy is released. But if you only do this for one atom, this is not really much yet. So you need to do this for a lot of atoms at the same time, or at a short period of time, to really have this impact of a huge bump. And what is done to achieve this is that when this process occurs, there are also neutrons after this division of the separation of this nuclei is achieved. There are also neutrons that coming out of this process usually. And if one manages to keep these neutrons in some area, and even manages to get them to stimulate other nuclei as the first nucleus was stimulated, then you can have this chain reaction where neutrons are emitted and splitting other atoms and so on, and then this chain reaction happens, and then you get all this energy released, which will in the end lead to such an atomic explosion. And this really releases high temperatures. So it's temperatures in the area of 1,000,000 degrees Kelvin. So it's really hot, and it's even hotter than the energy hotter than the temperatures inside of the sun. So it's really, really hot temperatures. But as it turns out, so it's a really powerful bomb, and it was really devastating in its impact. Also, when it was first tested in the Trinity test in New Mexico, it really is a powerful bomb, and was up to this point the most powerful weapon that was ever invented and ever tested and ever used. But it did not stop there. So there is even a more powerful way to create those bombs, by not using nuclear fission but nuclear fusion. And this has been done also later. Also the movie relates to that later they built this so-called hydrogen bomb, or the H bomb. And what is used there is not this nuclear fission, but it's the nuclear fusion. And there you use heavy hydrogen or deuterium and tritium, and they fusion to helium. And what happens there is, when these two nuclei are put together to one nuclei, to helium, there this effect occurs such that you again have such a mass defect, and with that even more energy than in the nuclear fission is released. And this needs a lot of temperature, or a lot of pressure, and really high temperatures. And to achieve such high temperatures and such a high pressure, you actually need an atomic bomb to ignite such an hydrogen bomb. So to ignite or to kindle an hydrogen bomb, you need an atomic bomb. So this shows how powerful this bomb actually is. And when this bomb was first tested in an atoll in the Pacific, this first test was called Ivy Mike, or the bomb was called Ivy Mike. And when it was tested in the Pacific, the island on which it was tested was, after the explosion, completely vanished into the Pacific. So this shows you how powerful such an explosion is and was. And it shows you also that how much more powerful than an atomic bomb that even is. So this was the physics, I think, or some introduction to the physics behind this atomic bomb that was created in the Manhattan Project, and also later in later projects of the atomic program of the US. And what I found most interesting about this Manhattan Project was that there were so many brilliant scientists that came together there. If you especially see it later, many of those received Nobel Prizes for their research, not on the atomic bomb, but on parts of particle physics. For example, Enrico Fermi was a physicist who for his work on nuclear fusion fission received a Nobel Prize, and Richard Feynman was a physicist there who received a Nobel Prize for his work on quantum electrodynamics, and many brilliant physicists were gathered there together. And what excites me most is the stories that are told that they had that occurred there in these times. For example, Enrico Fermi was really known for his great way of making estimations, and there is this area of what you call Fermi questions. Those are questions that you can state where you cannot immediately know the answer by just putting in some equations and calculating it out, but where you have to make some assumptions, where you have to make some estimations, some smart estimations, educated guesses to come to a close approximation of the result. For example, one was that we had in our when I started studying, it was one of the first homework I got was on these Fermi questions, and one of the question was how many dentists are there in Germany. And the way you can estimate this is you can say, for example, okay, I know there are about 80 million people living in Germany, and then you can from this conclude how many. So in Germany it is recommended to go to the dentist twice a year, and then you can see, okay, how many appointments would be needed for to cover all Germans who go to the dentist twice a year. And from this you can kind of estimate how many dentists there would be needed. And then this is how I calculated it. And what I missed is that, of course, not every dentist is working overtime and so on. So there is a little bit less dentists, a little bit more dentists than this absolute number of at least needed dentists. So I think in Germany it's about 80,000 dentists that are working there. But this is, I think I was in the right ballpark. I was at some 10,000s of dentists. So it was pretty accurate. And Fermi was really an expert on this. And this was shown in the fact that before the first atomic bomb was tested in this Trinity test in New Mexico, he started making such estimations about how much the impact will be, what it will look like, and all these questions. And using his technique, he estimated it, and in the end, he came pretty close to the actual results. So this is pretty interesting. Also, if you know about Richard Feynman, who really is, especially due to his Feynman lectures later and his unique way of looking at physics, he is really one of the stars of physics, or one of the greatest minds since Einstein, many people say. And if you have read his Surely You're Joking, Mr. Feynman, so it's kind of his autobiography where he tells about anecdotes about his life, also his life in the Manhattan Project. And there are many, many interesting stories about that. For example, he used to write letters to his wife using a secret language, and then he needed to decrypt it to the secret agents there who were concerned about the security, about the no secret information got out of there. And so he had, because he did these games with his wife, he had to explain to them what he was writing there actually. And what he also came up with in this time, he started the walls they had there. He started to hack them, to hack the locks and so on. So he was a really interesting character. And what's one interesting part, so in the movie Oppenheimer, he's not really part of it. He's kind of standing there and does not say much. But I think one part was really covered in the movie, and this was shows how much of an understanding and a deep trust Richard Feynman actually had in physics, because when the atomic bomb was tested first, everyone, as you can see in the movie, everyone is picking up his glasses to keep the radiation from harming their eyes and so on. And Richard Feynman did not do this. He wanted to see the explosion in its fullest, but he of course also wanted to protect himself. And what he said is, okay, I know from physics that all this harmful radiation, this UV light and so on, is not able to pass through glass. So if you know the spectrum of light passing through glass, it's interesting that the UV light is usually completely blocked out of it, and Feynman knew that, and so he just sat in a car where there's a windshield and there is a glass to protect him, and he looked at the explosion without putting any protection glasses in front of him. So this shows what a deep understanding of physics he actually had, and also a trust in the laws of physics that he knew so much about. So this I thought was really also interesting. So I really, if you want to know more about Richard Feynman, I really recommend you to read his book. It's really entertaining, really amusing, also to get deeper into the thinking of him, how he thought, how he was thinking about the world, because I think he had many right ideas about science and how science works, which is why I also cover much of him or much of his thoughts in my book, Sci-Faith, the compatibility of science and faith. So in the beginning, there's always a quote of some scientist or believing scientist, and many of those are from Feynman himself, although he himself was not believing, but still he had, I think, a lot of ideas about science that were pretty fitting or pretty accurate. And also, therefore, in a later episode, I plan on covering him there, covering his ideas, his statements, as I did also sometimes before when it fitted to the topic of the podcast. But I really encourage you to read more about him. And if you want to learn about he teaches physics, I really recommend to you the Feynman lectures. He dives in really deep, so it's really, it's meant for physics students, of course. But I think there is something like, it's called 6 easy pieces, where you basically get the introductory part of these lectures and the easy parts, the parts that are more easy to understand. So if you say, I don't want to dive in that deeply, then I recommend those to you, and then you can really grasp the thinking of him, how he understood things, and in which way his genius kind of worked. So it's really really encouraging to read those. Episode 20, The Music of the Big Bang. So I like to listen to a podcast from, it's called Why This Universe. It's also about science. It's from Shalma Waxman and Dan Hooper, who's from Fermilab in Chicago. And they, in the last year, covered an interesting topic, I think, about the music of the Big Bang. And I want just to sum up what they are talking about and what I took from this for as an analogy to the faith or to creation and so on. So let's just dive into it. So first of all, what is meant by Big Bang? So there are different things you can look at it. So there's the scientific description of the Big Bang, of course, where it says if we have this expansion of the universe. And if we just say, okay, is what it was expanding all the time, then it must have been at one point in space at one time. And then we get to this point at 30-something billion years ago, 30.8, I think, it must have been clumped all into one point. And from there, it exploded into all this universe that we have today. And of course, this, in one sense, puts a really atheistic point of view, that the universe came into existence spontaneously by such a big bang and so on and so on. But actually, I don't believe that really to be the case, because if you look into how the Big Bang Theory came to exist. It was actually a scientist called, not only a scientist, but a spiritual man called Georges Lemaitre. So he was a priest, and he was also working as a scientist, and he came up with the idea of the Big Bang. So it was there, you see, there was no contradiction for him to his faith. And also the Big Bang Theory was for a long time rejected because of this closeness to the creation account, to the beginning of the world, because before people always believed that that the world has been around forever and ever and ever and so on, and that the Bible telling about the beginning of a world was just nonsense. And with Lemaitre stating that there might have been a beginning of this universe in a Big Bang, it was actually coming closer to what the Bible says about how the creation came to be. So therefore, I think it's really closer to belief, actually. And also, if you look, say okay, but there are disagreements with what the creation account says and so on. But I think even if you look into the creation account, you clearly see that there's a beginning and there is the universe that is being created, and this must have somehow happened in a way that the materials came into existence by the word of God, of course. But then there is this case that is happened and this occurred, and therefore it has to start it by a bang in any way. So to say it like that, and even or especially if the world was created, then there would also have been such a beginning, such a big bang at the beginning, and maybe it's described in a little bit different way, which could be because there is leeway in how the Big Bang occurred, because it's an active field of study, and there's much known by now, but there's also not still much unknown by it. So there is a little bit of leeway what could actually have happened there. But so when I'm talking about the Big Bang, I basically mean the scientific part of the beginning of the world. So that what happened in the material during this time when the world came into being. So now you might think about, okay, now we have talked about a Big Bang, but what about the music of the Big Bang? I thought there was no sound in space, and you are actually completely right. So in space is a vacuum. So sound is something that needs a medium to transfer through to be able to pass. So sound actually on a physical level are fluctuations in pressure and density, and those necessarily need to be in some medium, in something like air or water or wood or something else. And therefore in space there cannot be no sound because there is no medium that can transport this sound. So whenever you watch a science fiction movie and they are having some space battle in somewhere in space and shooting at each other, and it makes sounds like pew pew and so on, then you know that this is not scientifically accurate because this would not occur. It would be completely silent. In space it's completely silent because sound has no way of being transferred, of being carried from one place to another. So therefore in space there is no sound, of course. But at the Big Bang, matter was so condensed, so densely put together that there was sound, actually. That's what they say there. And there was by gravitation and pressure, they worked against each other in differently dense regions, and with this they this yielded such sound waves to coming forth, and these sound waves were then created. And this is what they call the music of the Big Bang, because then it really gets interesting if you look deep into it. If you also account for the fact that the universe is expanding, and then you come to this occurrence that in regions of similar density, the same kind of sound waves are emitted. So the same frequencies of sound waves are emitted, and not only are they emitted? They are emitted at the same time. So you can really imagine it as some kind of choir where from different directions the same kind of sound is emitted and comes together in unison. And I think this is a really beautiful picture of the beginning of the world, that it's really kind of a choir, kind of a song, kind of music that is in there. And I think this is a great, for me, it's really also a sign that it has to be created, that there has to have been a creator behind it, because the Bible also tells us that the world was created by God's word, and there you have it. Word is also sound, and I mean, it can also have been some kind of music, you know. It was the spoken word of God, but it definitely had some music to it, and therefore you can see it also in the scientific part of the Big Bang, as I described. You can see that there already was this music present, or this music actually physically occurring, and therefore I think it's not much to make this step that when it says that the Bible describes this from a spiritual standpoint, and then we see it even manifested in the physical. I think this is pretty, for me, it's a pretty obvious sign that the world was really created by God. And you can also see in this, I think, so there's this scripture in the Gospels where the people are worshiping Jesus, and some take offense on this, and then Jesus says, yeah, if they don't worship me, then the stones will cry out and worship me. So there it says also that it is implied that creation yearns to worship God, worship the Creator. And I think this is what you see also here. It is a music in the creation as it comes about, and it really is about to be described like a choir, like music, like something that gives worship to the one who creates it. And this is, I think, also a really powerful statement. Also shows how the creation always reflects back upon the Creator, which is a principle that I often in this podcast also cover. So I think it's a really powerful sign for really that our world was really created by God. And also that the Bible is the correct description of this, and also a sign that really everything in this world yearns to or longs to worship God, its Creator, and that this has also been happening from the beginning of the universe on. Another speaking of this part of the creation reflecting back on the Creator, this is also often happening in mathematics itself, even if it is really a theoretical concept. Even there you have some concepts where God himself in this logical system is reflected in. And one great example of this that I found last year also was the example of Gabriel's horn, or Torricelli's trumpet, it is also called. And there it is, this is basically, you might know from school, these coordinate systems and the functions that you can draw in there. And one of the functions is the function of 1 over x. So you have a function where x is in the denominator, and as you might know, if a small number in the denominator, if there's a small number in the denominator, the number becomes really big. If there's a big number, it becomes really slow, and the bigger it is, the closer it gets to 0. And this is what the function 1 over x in this coordinate system will look like. So it will start from really high up there, from basically infinity, where it would be at 0, and from there it comes down and gets smaller and smaller and smaller until in infinity it would ultimately reach the point 0. So this is the way this function works. And now imagine you would put this into rotate this x-axis around and would put a rotation there, so that you don't have only this function, but you have kind of a form, kind of a form like something that would look like a trumpet or like a horn that is created by this, a three-dimensional figure. And now, if you use this thing and you try to calculate the volume of it, you will find that it has a finite volume. So you can compute a volume. It will be finite. I think it's pi, and but if you now say, okay, I know the volume, but now I want to calculate the surface. This you can also do by mathematical means, but then you can see that that you will have an infinite result. So the surface of it will be infinite, but the volume will be finite. And somebody therefore called it also Gabriel's wedding cake. And because you can, with some imagination, you can also say it looks like a wedding cake. And then he said, this is a cake that we can eat, but we cannot frost it. So you cannot put frosting on it because the surface is infinite and you would need infinite frosting, but you can eat it because the volume is finite. So this shows how counterintuitive this example is, and there are many such examples in mathematics, especially with fractal structures. For example, there is this example of a snowflake that you can draw using some mechanism or some algorithm where you're starting from a triangle or split it up at the sides and put in other triangles, and if you continue to this on and on and on, you will get something like a snowflake. And if you continue this infinitely and compute this structure that comes out there, you will find that the area that this snowflake will cover is of course finite, but the line or the border around it, if you compute the length of it, you will find that it has an infinite huge result, so that it tends towards infinity. So this is the same basically in a lower dimension, in a two-dimensional space. Here we had it in 3 dimensions, but this you can find several times in mathematics. And I think the powerful thing to me that it shows regarding the faith is that, as we know, God is infinite, but he, if we are believers, then he is living inside of us. The Bible clearly tells us this, and this can be, you can visualize it for yourself if you ask yourself, how can I, as a finite being, contain an infinite God? And this can be visualized in this way, that just as this Gabriel's horn has a finite volume but an infinite surface, I, as a finite human, can have an infinite God living on the inside of me without this being a contradiction. So this is, I think, a really powerful image on that, where you can visualize something like this easier. So this is also really the cool thing about physics and mathematics and science, that many things that are known in faith, or that seem in our faith to be contradictions, can be resolved even in physics and science sometimes. Or you can, if to visualize something, to get an understanding of some spiritual context, there is, since we have this concept of the creation reflecting itself in the creator reflecting himself in the creation, you can sometimes get an understanding of these things by looking at such occurrences. Of course, it's only a reflection, it's not a perfect image. This you have to keep in mind, but I think it's really helpful sometimes to have these reflections and to see the creator in its creation. So that's everything for today's episode. I hope you liked it and you enjoyed each part of it. If you want to get in touch with me or discuss a topic or want to give me some feedback, then feel free to contact me using the contact form on my website, sci-faith.de/en. And there you can go to the contact tab and contact me. And if you have any other things or episodes you want to have covered there, or topics you want to have covered, feel free to contact me there. Also, if you are not yet familiar with the format in which this podcast is produced, let me just briefly explain it to you. So there always at the beginning of a month or of a block, is a big block of 4 episodes in one thing. It's kind of like a preview, which I call it, where you have the next 4 episodes all in one episode together, combined. And this is for people who like to hear long format podcasts, who have a long way to work or something else, where they can listen to a long episode and can then have a preview of the next 4 episodes all at once, and are completely up to date from the beginning of the block. For those who like their episodes shorter, who prefer it if they have a half an hour or even less of a podcast episode, for those there is every week afterwards will appear a podcast episode almost in that length, and this way I can publish every week a new podcast every episode, and everyone can have it his own way, either once a month a long chunk of content, or once a week a shorter format podcast episode. So I think that's the best way for everyone, and also for me when I'm producing it. Please also note that this is an independent podcast, which means that it is recorded, produced, and marketed by me. So I really need your support in this. So if you like this podcast, then give it a 5-star rating. And if you have the time, even write a review to it. This just helps other listeners to become aware of this podcast. And then people who might be interested in this content can become aware of it. Also, if you have friends who you think would like this content, then recommend it to them and share it with them. Also, you can support me in other ways, for example by reading my blog and subscribing to my newsletter, or even by reading my books, which you can find on Amazon. For example, there is my latest novel out now is Alien Thoughts, which is pretty entertaining from the feedback that I gotten, and so it's also in some way related to science and faith. The topic of it is also in there, but of course you can also read the book to this podcast, Sci-Faith, The Compatibility of Science and Faith, which is also available in English since last year. Thank you for that, and now I wish you a wonderful day, and I'm looking forward for you to tune in again next time.